Okay, so let us continue our task of finding permutation representation next for the dihedral group of order 2n. Okay, which we already know from exercise 17 of section 2.6. So the first thing we are going to do in this solution is that we are going to have to rename the elements, which will actually help us identify, or in fact in finding out those functions tau g that are in fact going to give us, of course, the permutation representation. So let's see how we can rename the elements and what help that will provide us. So we start like this. We know, so in this exercise the group has been named G. So we call it G. G is the set of all elements Ci as I varies from 1 through 2n, but we don't know what these Ci's are. In fact, these Ci's are a way of renaming the elements. Now we are going to define the Ci's, where Ci is defined to be x0 yi minus 1. This is something we recognize, and it's an element in the dihedral group. In fact, if you think of the geometric realization of the dihedral group of order 2n, where it is the group of symmetries of a regular n-sided polygon, then this type of elements are the rotational symmetries. If I lies in this range and Ci is defined to be x1 y I minus n minus 1. If I lies in this range, if I is greater than or equal to n plus 1 and less than or equal to 2n. Now before we write anything else, before we go any further, let us see what we are getting. Are we really getting all the rotations here? What happens when we take I equal to 1? We then get x0, y0, which is the identity element in the dihedral group, which is actually, it does nothing to the polygon, but you can also think of it as rotating the polygon by 0 radian. If you take I equal to 2, then you get x0, y1, which corresponds to rotating the polygon either clockwise or anti-clockwise through an angle 2 pi divided by n radian. And then you increase the value of I and you get the other rotations, and the largest one, if you take I equal to n, then you get y n minus 1 or x0 y n minus 1. That is the largest rotation. And then what happens if you take I in this range? Then you get all the reflections. So one of those reflections is just the reflection which corresponds to x, right? And that you get for the value I equal to n plus 1, because then you get x1 y0, and then your I increases, so this superscript also increases, and eventually if when you take I equal to 2n, you get yn minus 1. Okay, so you get x1 yn minus 1. So you have all the rotations and all the reflections. That means these are the elements in our dihedral group. They have been given some other names, Ci. Okay, now what do we do with these Ci's? Now let G be this n cycle. C1, C2, C3 like that up to Cn, and H be this other n cycle consisting of the remaining Ci's in their natural order, I mean in the natural order of the subscript values 2n, and these of course are n cycles in what? In the permutation group of G. In the group where we consider the permutations of these symbols, these elements in the dihedral group themselves. Okay. Then one can verify that in A of G, in this group, which because it is the permutation group of 2n symbols, it's isomorphic to S2n, the symmetric group of degree 2n. In this group, these things happen. Tau Ci. So now we are going to write what these functions or what these permutations are. Tau Ci, it turns out, is equal to G to the power I minus 1 times H to the power I minus 1 when your I lies in this range. Okay, so that's why we have chosen these two particular n cycles. And these verifications that this is really the case, they are left to you. They are left to you because we have, by now we are well familiar with this kind of things. So I will just simply write the things down and it's up to you to verify. And also keep one more thing in mind, that because I have found these things out, so maybe there is some inadvertent mistake. So if you come across any mistake, please let me know. But that does not cover all the I values. We still have I in this range. So what about those Ci's or those tau Ci's? So they are coming next. Then tau C, which however we write a little differently, n plus I, that will be equal to C, it will be a little long, C1 comma Cn plus I, this 2 cycle times C2 comma Cn plus I minus 1, and it goes like that. And eventually it reaches Ci, and then here we have Cn plus 1. Then Ci plus 1, this one becomes C2n. Here the pattern changes. I mean, what is happening here, of course you can understand. When you have 1, you have n plus I. When you have 2, you have n plus I minus 1. That means from this suffix, you are subtracting 1 less than this suffix. So that when you have I here, then you are subtracting one less than I, which is nothing but Cn plus 1. But the moment you hit Ci plus 1, the pattern changes. It becomes C2n. That's just the way it is. And all these things you need to actually verify. Okay. the way we did previously. But then it goes on, and the next one is Ci plus 2. Now it starts to decrease. C 2n minus 1, and this way then it goes on, and eventually we reach Cn plus 1. But for what type of i's do we have this kind of tau functions? When your I lies between 1 and n minus 1. For that kind of I, and keep in mind the status of I here and the status of I here, they are a little different. Here I is just I, the suffix that represents the element or that gives the element Ci. Here, however, I is not the suffix that is giving the element Cn plus I. N plus I is that suffix. So as I varies from 1 through n minus 1, Cn plus I takes these values, Cn plus 1, Cn plus 2, and it goes like this, and when you take I equal to n minus 1, you get C2n minus 1. So here you have covered C1, C2, C3 all the way up to Cn, but then here, then next you have Cn plus 1, Cn plus 2 like that to C2n minus 1. So that leaves us with 1 remaining, which is C2n. For that, the tau is a little different. And that one is this tau C2n. Everything becomes extra complicated because here n itself can also change. It's a parameter for the group. For a given n, of course, you have one dihedral group, but as you change n, the order of the group changes and everything else also changes. But there you have the variable also here, Ci, but that's the way it comes out to be. What can we do? It looks complicated, but it is just what it is. So this one is right from the very beginning, it's C1, C2n, then C2, C2n minus 1, and it goes like that, and eventually we get to Cn plus 1. Again, I am repeating because the situation is very complicated and verifying it also will likely confuse you. So my advice to you, if you are trying to verify that these things are okay, is for you to take some specific value of n and then see what happens to all the i's. See if you are really getting these things, and then change the value of n, and then say you have checked all the calculations for say 5 or 6 values of n. Then you think of the general case. From that, those calculations, you will see the general pattern, and from there you will be able to see that yes, this should generally also be true. In fact, that's how I found these things. So the rest, of course, is just a matter of writing. So with this, the permutation representation of G is this homomorphism, which actually is going to be an isomorphism from G into A of G, which is isomorphic to S2n, and the function is of course Ci. We can write Ci because that's how the general element in the dihedral group looks after we have defined them this way. So this is tau Ci. So this group element here gets mapped onto this group element in this group, which itself is a bijection or a permutation of the symbols in the dihedral group. So that is the permutation representation. Okay, so let's now move on. Now we are going to see another kind of representation, which is given by the mappings lambda G instead of tau G. And they are going to give us the second permutation representation. So before the exercises come, there is a small paragraph. Let us call the realization of a group G as a set of permutations as given in exercise 1 of the previous section. Of the 9th section, the second permutation representation. Now let's recall what this thing was, and then we will start the exercises related to this notion. You remember that in the previous section, after proving Cayley's, in fact in the proof of Cayley's theorem only, we came across these functions tau G, right, which are maps. So if your small g is a group element, then tau G is defined to be a map from G to G, defined like this. For any group element H, tau G, if you apply it on H, that means multiplying H by G from the right hand side. And it turned out that this itself is a permutation of G and hence an element in the permutation group of G. So that's how we obtained the permutation representation. Now, in the first exercise of the previous section, we came across some other maps also, lambda G, which were defined like this. H lambda G is equal to, this time what we are going to do, we are again going to multiply H or take the product of H and G. But this time we are going to multiply H by G from the left side. Maybe because it's left, so I think it is being called lambda. lambda for L, Greek L, so GH. So just like the tau g's are permutations of G, lambda g's are also permutations of G, which is very easy to verify. So now if someone thinks of a map from G to A of G, just like this psi is a map from G to A of G, which maps every element to the corresponding tau function. Now this zeta, let me call it zeta for no reason actually, just a name. If this function maps every group element to the lambda function, that is G zeta is defined to be equal to lambda G, then this map is called the second permutation representation of G. Now we will be asked to find the second permutation representation for some given groups. So let's see next. So these ones involved multiplying everything by some group element from the right. This one is from the left. That is the only difference. Oh, but before, okay, so there is a very easy exercise here. This 23rd one, show that if G is an abelian group, then the permutation representation of G coincides with the second permutation representation of G. But that is almost evident, no? That is because if your group is abelian, then whether you are multiplying from the left or from the right, it does not matter. You are going to get the same thing. That's why each lambda G is equal to tau G, and conversely each tau G is equal to lambda G. So the zeta function and psi function, they are identical, they are the same. Of G, i.e. in the notation of the previous section. In fact, we have been using that notation only because tau G we have been using so far. Lambda G is equal to tau G for all G belonging to G. Now, because this exercise is just simply a matter of drawing our attention to this fact that for abelian groups, the second permutation representation actually does not give us anything new, and it's almost self-evident. So we are just going to write the solution also like that. It's evident, and that's just it. So let's now go to the actual calculations of the second permutation representation in some groups. Let's see exercise 24. Find the second permutation representation of S3. And also verify directly from the permutations obtained here. And exercise 20. That lambda A tau B is equal to tau B lambda A for all A and B belonging to S3. If you recall, in the previous section we proved, in fact I think in exercise 2, that any lambda commutes with any tau. So here we have been first of all asked to find the second permutation representation of S3. So it requires us to find all the lambdas, and then we have to verify directly from that calculation and from the tau functions that we already have found in exercise 20, where we found the permutation representation of S3, that this commutation is in fact true. Okay, the verification should be done directly. So let us first calculate the second permutation representation. So we just straight away write the lambda functions. In the permutation group of S3, which is isomorphic to S6 because there are 6 symbols, these are the things that we get. Lambda E, just like tau E, is just E itself, but again keeping in mind that this E is the identity element in S3, whereas this E is the identity element in AS3, that is S6. So that is one thing. And then lambda phi. So that means if we are multiplying every group element in S3 from the left side by phi, then that function gives this permutation lambda phi, which turns out to be this. The 2 cycle E comma phi times phi psi comma psi times psi phi comma psi square keeping in mind that this phi and psi are those things that we have um, in the description of S3 that we get when S3 was introduced for the first time. And I also discussed about why I am using this description here, or rather this way of writing the elements here. Because if you write them using the standard notation as cycles, then it becomes extremely long. Anyway, so the next one is lambda phi psi. So this is E comma phi psi. I should not make any mistakes in at least copying it from the notebook. Psi phi. Well, it's not a note, but it's a workbook that I keep. It will be replaced with another one when I run out of pages. So it's nothing permanent. So the next one is this. Lambda psi phi is E comma psi phi, then phi comma psi times next the 2 cycle is phi psi, consisting of the remaining symbols phi psi and psi square. Are these two the same? No, they are not same. Here we have a difference. How can they be the same? Next, lambda psi, let me write it here itself. Two more are left, lambda psi and lambda psi square. So lambda psi is a product of 2 3 cycles. E psi and psi squared, that is 1 3 cycle, and then phi, should not mess up the order, phi then psi phi, and then phi psi. And I think this order changes in the next one. And then finally lambda psi square, and the here also the order changes. The symbols, however, stay the same in a given cycle. So this is E psi square psi this time, and here in the next one we have phi psi and then psi phi. Okay, so that's just it with this. The second permutation representation of S3 is, let me keep calling it theta, from S3 into A of S3 and A of S3 is of course isomorphic to S6 such that G zeta is defined to be equal to lambda G. But we are not done yet. We have to verify this. Of course, we are not going to do that for every possible pair. We are just going to, I'm just going to show one, and the rest is left to you. Now, one can verify that we have this lambda phi psi times tau psi is equal to, it becomes a 6 cycle. This 6 cycle E psi phi, then psi square, phi psi, then psi, and then phi. And one also finds that this is equal to tau psi lambda phi psi. There is no particular reason for choosing these two particular lambda and tau functions, that is for these suffix g elements, S3 elements. But it's just one of all the possibilities. So the others you can verify. Similarly, the others means the other equations can also be verified. And here now the solution ends. Now let's see the next one. The next one is 25. Find the second permutation representation of the group defined in exercise 21. And if you go back to exercise 21, you will see that this group is that group of quaternion units. It's that 8th order group having those elements E, theta, A, B, C, theta A, theta B, theta C, that thing. Okay, so we just simply directly write in A of G, okay, it has been given a name, A of G, which is isomorphic because there are 8 symbols, S8. So in S8 we have these calculations. Again, lambda E is of course just E, it's always going to be that in any group, just like tau E is E. Then lambda theta, okay, this one is E theta, A theta A, B theta B, C theta C. Let me again repeat, there may be some mistakes in these calculations. Just maybe. Okay, I did these things very carefully, but still mistakes can happen, and they do crop up here and there every now and then. So please verify these things before you use them somewhere else. Okay, next, lambda A. Lambda A is this permutation, EA theta theta A. And another 4 cycle, BC theta B theta C. Then lambda B. Lambda B is EB theta theta B, and then A theta C theta A C. Then lambda C. Let me first write these things down, and then I will tell you about a mistake that I later on noticed in one of my videos regarding this thing. It's not something, it's not a mistake that is there in the written solution, but I said something wrongly. Okay, so I am coming back to that. EC, and it's about this group, the group of real quaternion units. AB theta A theta B. You can see that this looks a little suspicious. BC theta B theta C. For C it is AB theta A theta B, but here suddenly A theta C theta A C. So this part, at least this one, you definitely verify. I will also do, if this turns out to be wrong, then I will write the correct one in the comments. But anyway, so let's now write the other ones. Then lambda theta A is E theta A theta A. And then B theta C theta B C. Then lambda theta B is E theta B theta B. Then AC theta A theta C. Also, we do have some sort of difference. AC theta A theta C. Hope everything is correct. And the last one is E theta C theta C and A theta B theta A B. With this, the second permutation representation of G is zeta from G to A of G, which is isomorphic to S8, and Zeta is of course defined like this, G zeta is lambda G. So this is the solution, but now let me come back to the mistake that I was talking about. When we discussed this group of quaternions in the previous video, I think we did it in the previous video, or wherever we discussed it, I said something like this, that already you have the ring of real quaternions where, let me just simply call it R. The symbols are like this, A plus Bi plus Cj plus Bk, where A, B, C and D are real numbers. Now there is a very straightforward addition on this set of symbols that turns it into an abelian group, and there is a very complicated, arguably quite complicated multiplication also defined on this set, so that with these two operations this R forms a ring, and in fact it forms a division ring, okay, one in which every non-zero element is a unit, has a multiplicative inverse in the ring itself, but it is a division ring which has which is not commutative, so it fails to be a field. Now what is happening here is that here we are looking at a subgroup of the multiplicative group of this ring, because you see, since this ring is a division ring, if you collect the non-zero elements and consider this set under multiplication, then you get a group, and because it's non-commutative, this group is a non-abelian group. In this group there is a subgroup consisting of these symbols. These 8 symbols, which you obtain from this by taking one of them either +1 or -1 and the others 0. So you get these 8 symbols. This group is actually isomorphic to this group, and the isomorphism is very easy to establish. Under that isomorphism, 1 corresponds to E, -1 corresponds to theta, I corresponds to A. It does not really matter how we make this correspondence. J corresponds to B, K corresponds to C, and of course -I corresponds to theta A, -J corresponds to theta B, -K corresponds to theta C. But what is the mistake? The mistake is that since this group is called the group of quaternion units, okay, so I wrongly said that the group consists of the units in this ring. No, that is not true, because there are infinitely many units in this ring, in this division ring. Every non-zero element is a unit because it is a division ring, and by unit we mean an element in which has a multiplicative inverse in the ring. Here, however, we have only 8. So when we say that the group of all quaternion units, we do not really mean unit in the ring theory sense, but these special units, they are also units, but they are somewhat special because they give us or generate all such symbols in a vector space sense, but I am not going to go into those things. So that is the mistake that I made in saying things. anyway. So this is the solution. Now because we have been calculating second permutation representation, so why not the next one, because that is the last one. And the next is calculating the second permutation representation for the dihedral group again. So this time we need not again redefine the elements. We already have the Ci's. We just need to calculate the lambdas. So this is the next one and the last one for today. Find the permutation representation of the dihedral group of order 2n. So we straight away start like this. In A of G, okay, we need to write that we are using those notations, no? Otherwise the Ci's will be meaningless. With the notations from the solution to exercise (22), we have in A of G, which is isomorphic to S2n, these following things. So now we have the lambdas, and it turns out that the first n lambda Ci's are just the tau Ci's, that is g to the power I minus 1, h to the power I minus 1 for I varying from 1 through n. Next, this time instead of having a separate like what we had there, tau C2n was a little different from the rest. Here however, the very next one, lambda Cn plus 1, is a little different, and it turns out to be this C1 Cn plus 1, then C2 Cn plus 2, and so on up to Cn C2n, and then we have lambda Cn plus I, and it is C1 Cn plus I. Next, here it's going to increase, here it's going to decrease. Is it this thing? No, that was the previous one. Oh, so here this is also going to increase. This is so confusing. N plus I plus 1 and going like this we eventually reach Cn minus I plus 1 at some stage, and there we couple that with C2n. That's how it turns out to be. Am I writing it correctly? Let me see. N minus I plus 1 C2n, yes. And next N minus I plus 2, yes. But here we have Cn plus 1, okay. And then let's write one more, the next one, N minus I plus 3, so it should be Cn plus 2, yes. And then it goes like this, and finally we reach Cn and Cn plus I minus 1. And here the variation of I is like this, so that as we vary I from 2 through n, this varies from n plus 2 to 2n, so that this stays alone here, and we of course cover every Ci. So with this, the second permutation representation of our G. What is G? G is the dihedral group, is zeta from G into A of G, which is nothing but S2n isomorphically, and Ci zeta is lambda Ci. That's just it. So with this, in fact, the calculation of second permutation representations for whatever groups we have in this exercise set, that is over. Now after this we still have another kind of representation, coset representation, about which we will see in the next group theory video on Herstein's topics in algebra. So with that I end things here for tonight, and the next upload is this coming Friday, where let's go back to field theory. I think in field theory we already have completed solving one exercise set, right? And now we are going to start a new section, and in this section we are going to see how field theory can be used to answer some otherwise unanswerable questions in plain Euclidean geometry related to construction with straight edge and compass. Whether some figures are constructible or not, that question will be answered in a very nice and mysterious way using theory of field extensions. So with that we will see how far we can go on this coming Friday. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.